Okay, so you know now how to write electron configurations. You know how to write noble gas configurations. The whole point of that, the why, is not just because I want you to do it. It's because electrons are the basis of bonding. And if you want to understand how atoms get together to form compounds, you have to understand where the electrons are and what they're likely to do. But it's not all the electrons that are important. It's really only some of the electrons. We call those the valence electrons. And the definition of valence electrons are the s and p electrons in the highest principal energy level. That's the definition. So not all of the electrons are valence electrons, only the ones that are involved in bonding, and specifically only the ones that are in s and p sublevels in the outermost bonding shell. Okay, so only s and p electrons. No d or f electrons are considered valence electrons. Well, if you think about it, there are maximum 2 s electrons and maximum 6 p electrons, which means the most valence electrons you can have in an atom is 8. Now, if the number 8 rings a bell with you when you think about electrons in atoms, that's probably because you were told that 8 is like the perfect number. And it kind of is. So keep that in mind as we continue to learn about this stuff, because the number 8 is going to be very, very important when we talk about bonding. Let's get a couple of examples. So we'll take, for example, sodium. Here's sodium's electron configuration. There are 11 electrons, 1s2, 2s2, 2p6, 3s1. Definition of valence electrons is the highest s and p electrons in the highest principal energy level. Well, the principal energy level is defined by or determined by the large number that comes in front of the each little sublevel. So the 1, the 2, and the 3. The highest number is 3. There are only electrons in 3s, and there's only 1. So sodium has 1 valence electron. There are no 3p electrons here at all, so I don't count any. I only count the 1 in the 3s1. Sodium has 1 valence electron. Calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Again, highest energy s and p electrons. Well, the largest principal energy level here is 4s2. And there are only 2 electrons in the 4th energy level, and they're in the s sublevel. So we say that calcium has 2 valence electrons. We don't count the 3s or 3p because those are below 4. Sulfur, 1s2, 2s2, 2p6, 3s2, 3p4. Highest energy level is 3. The largest number in front of the sublevels is 3. And now we have some electrons in s and some in p. We have 2 in s and 4 in p. We have a total of 6 valence electrons for sulfur. Here's bromine, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. The highest number is 4. I'm going to take the 2 electrons in 4s and the 5 electrons in 4p. I do not touch the electrons, the d electrons in 3d. First of all, 3d is technically on the 3rd energy level and not in the highest energy level, which is the 4th for bromine. And second of all, we don't count d or f electrons. So bromine only has 7. Okay? Now, if you use the noble gas configuration, it's even easier to figure out the number of valence electrons, because the only electrons that you're actually writing out in a noble gas configuration are the valence electrons plus any d or f's that might be very high in energy. Here's an example. Let's take polonium. Polonium, symbol is PO. It has 84 electrons. Stop the video and write the noble gas or shorthand configuration for polonium. I'll wait. Got it? Here's what I've got. So the previous noble gas to polonium, the one right before it numerically, is xenon. Xenon is atomic number 54, and that's the noble gas that comes numerically before number 84. So xenon, and then what's left after xenon? Xenon has 54 electrons. We have to get to 84, so we need more. So we've got 6s2, 4f14, 5d10, 6p4. All of those are taken directly from the little diagram with the arrows so that I know what order to put them in. This might be a good time to point out that on your periodic table, if you look under polonium, you will see xenon, Xe, in brackets. And then you'll see 4f14, 5d10, 6s2, 6p4, which is all of the sublevels that I have here, but not in the right order. So yes, your periodic table has the noble gas configurations, but they're not 100% correct. They don't account for crossover. So be very careful when using that. If you use the ones off the periodic table, most of the time you're going to be wrong. Okay? All right, so let's take a look at polonium again. We have Xe, and then we have 6s2, 4f14, 5d10, and 6p4. Well, the largest or the highest energy, principal energy level is 6. That's the largest number I have here. I have 4, 5, and 6 there, but 6 is the biggest one, so 6. Only S and P electrons. 2 in 6s, 4 in 6p, that's a total of 6. Now, interestingly enough, the last example we just had, on the previous example, we had another element that had 6 valence electrons. That was sulfur. Well, look at polonium on the periodic table. Polonium is in the same family as sulfur, and so it has the same valence electrons as sulfur. Okay? Very simple to figure out the number of valence electrons in an atom. Now, because we're only interested in valence electrons, S and P, and we don't even want to get confused with the D's or F's, there's another way of writing, or in this case drawing, the information that we want to put down there, is specifically the valence electrons for an element. It's called a Lewis electron dot structure, and it was developed by a chemist, physicist named G.N. Lewis, and a very brilliant guy, also a very unpleasant guy from what I understand from reading. But anyway, very smart. And his work was done primarily in electrons, electron movement, electron behavior, and all of this. So you'll hear his name a few more times this year. Lewis came up with a way of indicating the information that we want about an element when it comes to bonding, which is its electrons. It's a simpler way to know the valence electrons, or show them. We use the chemical symbol for the element, so the letters, surrounded by dots. And the number of dots is equal to the number of valence electrons in that element. Remember, there's a maximum of 8 valence electrons possible, so there's a maximum of 8 dots in our dot structure. Now, the important thing about the dot structure is that the way I write the dots is very important, because it has to reflect the actual arrangement of valence electrons in their orbitals. And I'll show you what that looks like in just a second. Okay, so let's take a look at an example. So we'll use as an example chlorine. Chlorine's a good one. So chlorine has a symbol Cl. Its noble gas configuration, previous noble gas to chlorine, is neon, and after neon we have 3s2, 3p5. Okay, so this is the noble gas configuration for chlorine. There is my highest energy S and P electrons. That means there are a total of 7 valence electrons in chlorine. Okay? Now, in order to put the dots in around the chlorine symbol, I need to know what's going on. How are these electrons arranged in the 3s and the 3p? So I'm going to do a little orbital filling diagram right down here. There's the 3s. 3s has one box because it's one orbital, and there's 2 electrons in there, so there's my 2 arrows. 3p is just above it in energy, and that should have 3 boxes because the 3p orbital sublevel has 3 orbitals. They're all the same energy. And I have 5 electrons to put in there, so I go 1, 2, 3, 4, 5. Do you remember whose rule says that I have to put them in that way? Look it up in your notes if you don't remember. It's really important. So I have a pair of dots, another pair of dots, another pair of dots, and then 1 dot all by itself. I have a total of 7 dots that I need to put in here. So I draw my symbol. And if you can kind of imagine that this symbol is in a square has 4 sides. 4 times 2 is 8. So if we put pairs on any 3 of the 4 sides, like that, and then this 1 all by itself, I'm going to put here. So these are my 3 pairs. Okay, here's 1 pair of dots, here's another pair of dots, here's another pair of dots, and then my 1 guy by himself here goes over here by himself. Now, it doesn't matter where I put that 1 unpaired dot. I can put it on any side. It doesn't matter where you put it. All that matters is that the number and pattern of dots should be equal to the number and pattern of valence electrons. Let's try another example. So in this case, we're going to try oxygen. Okay, so oxygen has a noble gas configuration. The previous noble gas to oxygen is helium. And after helium, we have 2s2 and 2p4. Okay, there's my noble gas configuration. According to my rules for valence electrons, there are 2 plus 4, there are 6 valence electrons in oxygen. So I need to put 6 dots around the O, but I'd like to know how they're arranged. So I'm going to take a look again. In the 2s, it's an S sublevel. S sublevels always have one box, 2 arrows, because there's 2 electrons. 2p, we've got 3 boxes because there are 3 p orbitals. There are 4 electrons that have to go in there. 1, 2, 3, and 4. So I have a pair, and then 2 by themselves. So I draw my O for oxygen. I have 2 pairs and 2 singles. And it does not matter where I put the pairs and where I put the singles, so long as I can easily see that there are 2 pairs of dots and 2 single dots to represent that. That's all there is to it. It's very, very simple. Writing dot structures is going to be very useful for you in the future, especially when we start looking at ions and when we start looking at how to draw molecule structures. So rewatch the video, take good notes, pause and rewind when necessary, and ask questions in class if you're not sure how to do it.